Hi, I am back again from MySlate, and in this video we will move on. If you remember, we were discussing the applications of derivatives in the previous video, and we looked at the rate of change of quantities. So here we will move further and discuss another kind of applications of derivatives, which is how to find equations. And let's look at two simple examples further to appreciate this. So example 1 is about finding the equation of a tangent, and the curve is given to us. It has this expression, and every time it may not be possible to quickly draw the diagram of the figure of the equation of the curve. If you can do that, that's great, but every time you may not be able to do that quickly. So you should be able to follow logically the procedure that we just saw. So here our task is to find the equation of the tangent to this curve at a particular point where this curve cuts the x-axis. Okay, so here we need to do two things before we can find the slope of the tangent. First, we need to find this point, the coordinates of the point where this curve cuts x-axis, and then we also need to find the slope of the tangent to this curve on that point, which means the value of dy by dx at that particular point, and then we can find the equation of the tangent. So let's start. So we have this equation of the curve, and please note here, always keep in mind the points where this is not defined. So because this curve, we already know this function would not be continuous at those points. So the denominator vanishes at these 2 points, x equals 2 and 3. So we are talking about every point other than those 2 points. The points which are in the domain of that function, and we can see that because numerator and denominator both are polynomial functions, so except for x equals 2 and 3, this function is continuous everywhere else on the real line. Okay, so let's now find the coordinates of the point where this cuts x-axis. We know that y equals 0 everywhere on the x-axis. So we simply plug that back into the equation of the curve, and we can easily see that x equals 7 at that point. So the coordinates of that point are 7, 0. And now the other piece of information we need is dy by dx, that is the slope of the tangent at that point. So we need to do a little bit of calculation there, a little bit of algebra. So dy by dx, we simply take the derivative of both the sides with respect to x, and we use our usual formula for the derivative of a rational function which has a numerator and denominator. So see here we have the denominator squared, and on the numerator we have the derivative of the numerator which is x minus 7, which is 1, and multiplied by the denominator minus the numerator multiplied by the derivative of the denominator. And denominator, because it is a product of two functions, we again apply the product rule of derivatives to find out the derivative of the denominator, and then we further simplify it. And here you might be wondering where this y came from. Well, this is just a simplification. You don't really have to go all this far, because all that we need to do is plug in these values of x and y, 7 and 0. We could have done that even at this stage and found out the slope. But we are just simplifying it further. What we have done here is we have divided both the numerator and denominator of this expression by x minus 2 multiplied by x minus 3. So that's how we got rid of the square here in the denominator, and in the numerator we got this 1 here, and then here we could get y, because we know that y equals x minus 7 divided by x minus 2 and x minus 3. So that's what we got, how we got y here, and that probably just simplifies the calculation. But as I said, you need not have gone this far. You could have plugged in the value of x equals 7 right here. And now that's what we do here. We plug in those values and we get the slope of the tangent at that point as 1 by 20. And the remaining task is pretty straightforward. We plug those two pieces of information, the coordinates of x naught and y naught, and the slope of the tangent at that point, in the straight line equation to get the slope, the equation of the tangent. Let's look at the final example.